Hello everyone, welcome to this session number 19. In the previous session 18, we have discussed about the Gauss-Seidel load flow method that is an iterative approach to solve nonlinear equation. The Gauss-Seidel load flow method has linear convergence characteristics. It usually takes more time to converge if the system is large or big. It may not converge in some conditions also. Therefore, we go for another iterative approach to solve load flow equation, that is Newton-Raphson load flow method. Today we are going to discuss this. This is the second major power flow solution method, that is Newton-Raphson algorithm. This Newton-Raphson method is an iterative approach which approximates the sets of nonlinear simultaneous equations to a set of linear equations using Taylor series expansion, and the terms are restricted to first order approximation. And the key idea behind this Newton-Raphson is to use sequential linearization. If we see the general form of problem, that is that we have to find the absolute solution x such that f x cap is equal to 0. Now for a scalar variable, we will see the methods how we are going to find the solution using the Newton-Raphson method. First, for each case x cap xb, we define delta x, that is x cap minus x, and then we represent fx cap by a Taylor series about fx. So using Taylor series expansion, we define this function fx, and then we approximate this fx cap by neglecting all terms except the first two, that is this fxb and this first derivative of fx, and we neglect second derivative and the higher order terms. Upon solving this, we will get this one. So this is the and after doing this linear approximation to solve for delta x, and then we find this next new approximate of x cap using this equation. Now the second Now let us take an example based on this method, based on the scalar based on the scalar variable for Newton-Raphson method. So we have to solve this equation by using Newton-Raphson method. The equation is fx is equal to x square minus 2 is equal to 0. So we know this equation, delta x equation, that comes from after using the linear approximation of the Taylor series expansion of the function fx. We substitute all these values like dfx by dx, that we get 2x, and function fx, and we will get delta x, and then we will get new value of x, that is new iterative value of x, by substituting this delta x in the first equation, above equation. So now we have to just put the iteration method. We have to take the first iteration, second iteration, third iteration subsequently, and based on the tolerance limit we will get the final solution. So upon putting this on taking the initial case x0 is equal to 1, then we will solve the first iteration where we get these values, and this is the second iteration where we get these values, and upon third and fourth iteration we get these values. If this tolerance, if you see this fxb, then what is the tolerance limit? Based on that we can say that this is the final solution. So this is the basic of Newton-Raphson method. So what are the major things that we have to keep in mind for Newton-Raphson method? The first is that when close to the solution, the error decreases quite quickly. Because Newton-Raphson method has quadratic convergence, this Gauss other whereas this Gauss-Seidel method has linear convergence characteristics. So this one is very important, that Newton-Raphson has quadratic convergence, whereas this Gauss-Seidel has linear convergence characteristics. We will see this also on the comparison between Gauss-Seidel and Newton-Raphson methods. Because of this quadratic convergence in Newton-Raphson method, this method is quite mathematically superior to the Gauss-Seidel method and is less prone to divergence with ill-conditioned problem. Like we have a big system or ill pro, or if the system is large, then uh, this Newton-Raphson method is less prone in comparison to the Gauss-Seidel method. This FXV is known as the mismatch, which we would like to drive to zero, which we have to take it to zero. And the stopping criteria is when this FXV less than some tolerance value and the results are dependent upon the initial case. Here we can see this FXV is tending to zero. So upon fourth iteration, we can say that this is approximately tending to zero. So we may take this as the final solution. That this x value we may take it as the final solution if the tolerance limit is if whatever the tolerance limit is given that is coming within that part. Final solution if tolerance is satisfied. And these results are also dependent upon the initial guess how what you have taken the initial guess. Depending upon that it may takes more time or less time. If it is just the initial guess is just close to the final solution, then then it will take lesser time. This if initial guess is merge diverging, if initial guess is enough enough have a quite sufficient distance from sufficient distance from the final solution, then it takes more time. A solution regions of attraction is the set of initial guesses that converge to the particle solution, and the region of attraction is often hard to determine. Now let us come to the multivariable Newton-Raphson method. Here we generalize to the case where x is an n-dimension vector and fx is an n-dimension function. Again, similar to the scalar vector, similar to the scalar variable, here again we define the solution x cap such that fx cap is equal to 0 and delta x is equal to x cap minus x. Now we take the Taylor series expansion with respect to each fi x. So we will get f1 x cap and this Taylor series expansion of this f1 x cap and the Taylor series expansion of fn x we will get like this way. If you write this in form of the matrix form, then you will get in this way. And if you substitute this f1 x f2 x to the left hand side, then we will get this second equation for the in the matrix form. Now the n cross n matrix of partial derivative is known as the Jacobian matrix. This is the Jacobian matrix. So Jacobian matrix is nothing but it is a matrix of partial derivative. This is the Jacobian matrix. So whenever you are hearing this term, what is Jacobian matrix? So you have to just where this partial derivative matrix is present, that is the Jacobian matrix. You have to keep in mind. So this is the Jacobian matrix. That is the matrix of partial derivatives. We will see this. This is very important for the GATE exam. For the Newton-Raphson method, most of the questions have been asked from the Jacobian matrix part only. Now, similar to the scalar variable, let us take the example for the multivariable. Here we have to solve for x, that is x1 x2 such that fx is equal to 0, where these functions have been given f1x is equal to 2x1 square plus x2 square minus 8 is equal to 0. f2x is equal to x1 square minus x2 square plus x1 x2 minus 4 is equal to 0. First, symbolically, we have to determine the Jacobian. So in the Newton-Raphson method, for multi-variable problem, we have to first determine the Jacobian matrix. So first we have to determine the Jacobian matrix. That is delta del f1x del x1 del f1x del x2 del fx f2x del x1 del f2x del x2. Upon finding this Jacobian matrix, you will get 4x1 2x2 2x1 plus x2 x1 minus 2x2. Now substitute this value in for getting the delta x1 and delta x2, because this will take you to the another iteration. So delta x1 is the target for any any problem that consists of iterative approach. So for finding delta x, you have to find first the Jacobian matrix. We have found this Jacobian matrix, and after that we have to take the initial guess. So we have taken the initial guess as 1 1, x1 as 1 and x2 as 1, and upon putting all these values in delta x1 and x2 in this equation, we will get the first iteration. The first iteration, the first solution after doing the first iteration, we will get 2.1, 1.3, and subsequently we will go for the another iteration. Here we will get the solution as 1.8284 and 1.2122. And after after doing iteration, we check for effects to see if it is below our specified tolerance. So if we find this fx2, then it is coming as 0.1556 and 0.0990. And if this tolerance is 0.2, then we would have done. Otherwise, we would continue iterating. Suppose here we have assumed this, it is given that tolerance is 0.2. So here we can see that fx1, this f1x is 0.1556. It is also less than 0.2, and f2x is 0.09, is also less than 0.2. So this is the final solution. This is the final solution, that is x1 is equal to 1.8284 and x2 is equal to 1.2122. Because on putting these values, we are getting the f1x 0.1556 and f2x is 0.009, and both are below the tolerance limit. Okay. If any one of the is not coming within this tolerance value, then we have to do the another iteration. If both the f1x and f2x, whatever the variables you have assumed, and all the functions are coming beyond the within the specified tolerance value, then you have to stop there, and you have to take it as the final solution for the problem. Now we have seen the Newton-Raphson for the generalized case, like for the mathematics case, for the scalar variable, and for the multivariable. Now let us take the application of Newton-Raphson method to the power flow problem. So we have seen this equation, like you have to rewrite this complex power equation as equation with real coefficient. So SI VI conjugate SI VI, we know the current injection can be written as YIK VK, that is admittance matrix and voltage vector. So upon doing the conjugate, we will get yik conjugate, vk conjugate, and this we can put this in the polar form. Yik is equal to yik at the angle of theta ik. We have assumed this angle as theta ik and the magnitude as yik mod. And vi, we have assumed vi at the angle of delta I. And we know that e to the power j theta is equal to cos theta plus j sin theta. So upon substituting these values, that is vi is equal to mod of vi delta I and yik conjugate, that is yik minus theta ik, and vk conjugate is mod vk at the angle of delta k. So upon resolving the real and imaginary parts, we will get pi this one and qi at this one. So here you may think that we are getting minus theta, the angle term, the whole angle term. If you see here, k is equal to 1 to n, that is vi vk yik at the angle of minus theta ik minus delta k plus delta I. So here we have taken the negative because we know that cos of minus phi is equal to cos phi. So we can take this one as also. And here for qi, we have to take the sine term, but sine of minus phi is minus sine phi. So this negative sign comes out, out, out from the sine term. Okay, all right. So this is for balance power balance equation we have seen in the previous slide. Now this Newton-Raphson method, why we are going towards this Newton-Raphson method, else we have the Gauss-Seidel load flow method, because this is more efficient and practical for large power system. And the main advantage of this system is that the number of iterations required to obtain a solution is independent of the size of problem, and computationally it is very fast. So that is also one of the major advantage of Newton-Raphson method, that this solution, the solution we are getting is the number of iteration required to obtain a solution is independent of the size of problem. That the number of iteration does not depend on the size of does not depend upon the size of the system, and it is also computationally very fast. In the Newton-Raphson flow, we use Newton methods to determine voltage, magnitude, and angle at each bus in the power system. So we need to solve this power balance equation to get the voltage, magnitude, and angle at each bus in the power system. So what we do, expanding this power balance equation in Taylor series and neglecting higher order terms, we get this form. So here in the left hand side, we have put the we have put the active and reactive power mismatch, and in the right hand side we have put the angle mismatch and the voltage magnitude mismatch. So this power balance equation is very important, and this power balance equation you have to expand using the Taylor series expansion, and then neglect the higher terms. You have to just consider the first two terms only. So then you will get this expression. So here we can see that if you divide this into parts, like here all terms are all terms here are identical. There, that is, we can take it a Jacobian one, and in this active powers there is derivative of active power with respect to voltage magnitude. This we can take at J2, and in J3 this partial derivative of reactive power with respect to voltage angle, that is J3, and here partial derivative of reactive power with respect to voltage magnitude, so we can take it as J4. So we can write in simpler form also, if you don't write in like for each buses. So here one thing also you can note down here, we have not taken bus number 1 because we have considered bus number 1 as the slack bus, where we already know the voltage magnitude and the angle, phase angle for that bus. So here we have assumed this bus 1 as the slack bus, and the equation can be written in the short form like J1, J2, J3 and J4. Now, as similar to the Gaussian load flow method, this power flow is solved using the Newton-Raphson power flow method is the approximately similar. So here we have to set V is equal to 0 and then make the initial guess of x and xv. While doing this fxb, you have to find this by putting the final solution in function. If it is more than tolerance value, then you have to do the iteration. Then you have to do the next iteration, and if this function on putting the solution in the function, if you are getting less than tolerance value, then you have to stop. If in some iteration you are getting function this less than tolerance, then stop and take it as the final solution. For multivariable, you have to take the least square method or infinity. There are some techniques to take this normalize this function, and you have to calculate that value, and that you have calculated value you have to compare with the tolerance value. We have discussed in the Gaussian load flow method. There you can see the methods for multivariable, how you can find the find this least square method. Now let us see the decoupled Newton-Raphson power flow method. As we all know that transmission lines of power systems have a very low R/X ratio, that is approximately 0.1 to 0.001. For such system, real power mismatch are less sensitive to changes in the voltage magnitude and are very sensitive to changes in the phase angle. Similarly, reactive power mismatch is less sensitive to changes in the phase angle and are very sensitive to the voltage magnitude. Therefore, it is reasonable to set elements of J2 and J3 of Jacobian matrix to 0. Therefore, the previous equation becomes like this one. We have to make J2 and J3 as 0 because this real power mismatch are very sensitive to the phase angle only, and the reactive power mismatch are very sensitive to the voltage magnitude only. In the voltage control bus, the voltage magnitudes are known. So therefore, if m bus in the system, if m buses of the system are voltage control and n is the size of the system, then J1 is of the order of n minus 1. J1 means like here both you have to calculate the to calculate voltage magnitude and the angle, that is delta, and here J4 is the n minus 1 minus m because here you have to calculate only delta, to calculate only delta. That's why this one J4 is of reduced size. Now let us see the comparison between Gauss-Seidel and Newton-Raphson power flow method. So Gauss-Seidel, it requires large number of iterations to reach convergence, whereas Newton-Raphson requires less number of iterations to reach convergence. Here this computation time is less, but computational time for iteration is more. This is the disadvantage of Newton-Raphson method. This because this is quadratic convergence also. This computation time per iteration is more. Gauss-Seidel has linear convergence characteristics, whereas Newton-Raphson has quadratic convergence characteristics. In the Gauss-Seidel, the number of iterations required for convergence increases with the size of system, whereas Newton-Raphson is independent of the size of system. This is one of the big advantage for Newton-Raphson method. Uh, Gauss-Seidel method require less memory, whereas Newton-Raphson method require more memory because this one has more computation time, whereas Gauss-Seidel has less computational time. Now, the pa- uh, most important part for the gate point of view, we have to find the Jacobian matrix size. So there are 2 points that you have to keep in mind. The first point is that bus where a static var capacitor is connected, which maintain voltage at the connected bus is categorized as PV bus. So just keep in this mind. If it is written like in problem that a static var capacitor is connected at a certain bus, then you have to consider that bus as PV bus. And suppose if a bus is given where shunt capacitor and inductor are connected, then you have to take that bus as PQ bus, that is load bus. PV bus means generator bus, and this PQ bus means load bus. And the Jacobian matrix size is 2 into PQ plus PV cross 2 into PQ plus PV. So let us see the first problem. So a 183 bus power system has 150 PQ buses and 32 PV buses. In the general case, to obtain load flow solution using Newton-Raphson method in polar coordinates, the minimum number of simultaneous equations to be solved is. That means you have to find the size of Jacobian matrix. Here, number of buses, number of buses is given as 183 and number of PQ buses is given as 150 and number of PV buses is given as 32. So if you add this one, then PQ plus PV, then it is coming as 150 plus 32, that is 182. That means in PV they have not uh, they have not include the slack bus. So one is slack bus, one is slack bus. That's why in PV bus there are 32 buses only. So size of Jacobian matrix is 2 into PQ, 2 into PQ bus plus PV bus, 2 into PQ plus PV. So PQ is 150 plus PV is 32. So it is 300 plus 32. So it is coming as 332. So that is the minimum number simultaneous you have to solve is 332. That is the answer. So here why we have taken 2 into PQ. So because for PQ bus you have to determine both. That's why we have taken two times of PQ. You have to determine both, that is voltage magnitude and the phase angle. This is voltage magnitude and this is phase angle. While in PV bus, so for PV bus, you have to determine only one thing because voltage magnitude is already given. That's why it is coming as once only. You have to determine only delta, not the voltage magnitude. That's why Jacobian matrix size is coming like this. I think now you have understood. So this you take it as very for, important for a gate exam. Now this question is asked in gate trans. This first question I have not mentioned. So this is asked in gate 2014. It is of 1 mark and set 3. Now coming to the second question. In the load flow problem solved by Newton-Raphson method with polar coordinates, the size of Jacobian is 100 cross section 100 cross 100. If there are 20 PV buses in addition to PQ buses and a slack bus, the total number of buses in the system is. So the size of Jacobian matrix, we know that 2 into PQ plus PV bus. PV bus is 20 given, PQ bus you have to find, and Jacobian matrix size 100 is given. From there you will get the PQ bus is 40. So total number of buses will be PQ bus plus PV bus plus 1. PQ bus is 40, PV bus is 20, and 1 is slack bus. Therefore, you will get the 61 as the answer. Now third problem. In a 100 bus power system, there are 10 generators. In a particular iteration of Newton-Raphson Laod Flow technique in polar coordinate, two of the PV buses are converted to PQ type in this iteration, and the options are given. So the number of unknown voltage angles increases by 2 and the number of unknown voltage magnitude increases by 2. This is wrong. Why it is wrong? So PV bus are converted to PQ. So PV bus are converted to PQ. Here delta is unknown. Here only delta is unknown. Both V and delta are unknowns. So this delta, whether it is PV or it is PQ, delta is unknown in both sides. That means the number of unknown voltage angles remains unchanged. So this B option is correct, and also it is given that number of unknown voltage magnitude increases by 2 because this voltage magnitude is not given in the PQ type buses. So B is correct option. And if you see other option, then other option is that the number of unknown voltage angles increases by 2. That is incorrect because it remains same, and the number of unknown voltage decreases by 2. It is not decreasing, it is increasing. So these are incorrect. And the reason for this correct answer, correct option is B, because the voltage angle is the common variable for both PV and PQ buses, so it remains unchanged. Whereas voltage magnitude is specified in PV bus and not specified in PQ bus, so it increases by 2. That is the reason for this problem. Now coming to the last problem for today's session. Here, so I have not mentioned the gate here. So this problem is asked in gate 2016, 1 mark set 1, and this problem is asked in gate 2016, 1 mark set 2. So it is similar to previous question. Just you have to find the Jacobian matrix here only. A power system has 100 buses, including 10 generator buses. For the load flow analysis using Newton-Raphson method in polar coordinates, the size of Jacobian is. So we know that. So here what are things we have given? Number of buses is 100. PQ bus, that is PQ bus is 100 minus 10, that is 90, and PV bus is 10. So here we can say that it also includes slack bus, but in the Jacobian matrix you have to not include the slack bus. That is the you have to keep in mind. Size of Jacobian matrix is equal to 2 into PQ plus PV. It does not include slack bus. Therefore, size Jacobian matrix is 2 into 90. PV is 9. So 189. Therefore, correct answer is A. That's all. Thank you.